Hi, I'm Mark Pekka, manager of the Arizona LaserChron Center, and we're here in the beautiful Sonoran Desert just west of campus. And we're going to show you all the steps from collecting the rock to getting a final age in the lab. So this is a rhyolite, so it's going to be pretty rich in zircon. So the key is we're going to fill up a small bag like this, and just remember, no rocks bigger than the size of your fist. That's it, last rock, let's go get an age.
Hey, I'm Martin Pepper. I do everything in this lab from processing rocks to running samples on the new and the E2. And first thing we got to do with this is crush it down into gravel. The jaw crusher gets its name because it has plates with jaws and it quickly nibbles the sample down into gravel. Next, we dump it into a pulverizer chute, and the goal here is to take it down into sand. The last step is the Whiffley table, so it's essentially just your gold pan rolled out flat. Same grooves, going slightly uphill. We're now pouring our sandy sample, and our heavies will track their way uphill and make their way all the way down here into our foil boat. Everything else lighter will typically come straight off the water table. All right, we finished off with the Whiffley table. It's in our foil boat, all folded up. We're gonna take this down to Minsup, dry it off, hand it off to Galen.
My name is Galen Simpson, and I am the Mineral Separation Lab Manager. After we've used the HAD magnet to get rid of iron filings and magnetite from the sample, the next step is the Franz magnetic separator. You can see the sample pouring out of this tube. Here is the magnetic barrier. Magnetic minerals cannot cross this barrier. As you can see, the non-magnetic minerals are dropping down to this lower chute. The magnetic minerals fall into this dark cup. The light minerals, non-magnetic, fall into the silver cup. And then we take this to the next step. Now we're going to separate minerals by density using methylene iodide, which has a density of 3.32. Heavy minerals will sink to the bottom. Lighter minerals will float on top. So I'm going to pour in now our sample, and I'm going to stir, and this will allow the minerals to separate and go where they want to go. Now we're going to rinse the zircons with acetone to remove all traces of the methylene iodide. These are beautiful, clean, igneous zircons. They can go directly upstairs to the picking room.
Hi, I'm Sarah George. I'm a postdoc in the Arizona LaserChron lab, and I work in all steps of the process in the lab. Broadly, I'm interested in using different trace and rare earth element chemistries along with the ages that we produce in our lab to look at long-term mountain building processes. What I'm doing right now is I've picked some grains from the rhyolite, and I'm going to mount some standards alongside them. And we use those standards to bracket and correct the ages that we get off the mass spectrometer. So you'll notice that I'm sticking these grains onto tape currently. And after I've added all my standards, we're going to put a ring form around these grains, and then we're going to pour some epoxy in. And once that's set, that will allow us to transfer this disc. We'll sand down in about halfway into each grain, and then we'll send them off to the imaging lab to get high-resolution images.
Hey, I'm Nikki Geisler. I am working down here in the Scanning Electron Microscope lab. That's what this thing is. The secondary electron microscope is actually just a tungsten filament, like a light bulb, emitting electrons down the column and onto the surface of your sample, and emits into the CL detector, which is the cathodoluminescence detector, the energy dispersive spectroscopy detector, or the secondary electron detector back here in the back. And make sure that the sample fits underneath the column. So now we've got the beam on. We've got our infrared camera so that we can watch the position of the detector. I'm going to go ahead and install the CL detector. Done. All right, now we've started to scan. Here we have some beautiful magmatic zircons. But let me show you a CL image of a really cool grain. Now these are interesting grains. This is how the image comes off the scanning electron microscope. Let me invert the image in Photoshop so you can probably see this imagery better. You can see the inherited core of metamorphic textures, where these rims are igneous crystallization, and perhaps even a third event here. These grains have a complex history. Now that we've stitched the CL images together into one montage, we'll take it over to the mass spectrometer lab and run them.
Hi, I'm Elisa White. I'm a postdoc here at ALC, and I'm studying uranium series and strontium isotopes, and then trace and rare earth elements, both in rock and water. Once the samples are imaged and cleaned, they go into this 9-mount sample drawer, and then we've got both nitrogen and helium flowing through the laser. As the laser shoots the samples, the helium transports that into this Aris and then into our torch box. It turns into a plasma, which turns it into an ion beam. And then that beam is actually focused and sent through a 1-millimeter hole and into the lens box, which has several lenses that are really going to focus that beam before it goes into the magnet part of the mass spectrometer. The sample gets to our giant electromagnet, and that tries to bend the path of all of the isotopes. But those heavier isotopes can't bend as easily as those lighter isotopes because of the differences in mass. So then we are able to collect all of those isotopes in either Faraday cups or ion counters simultaneously, which is why we call this a multi-collector. So I'm analyzing those zircons from the rhyolite now, and in order to do that, we need to have our CL image. So that's what I'm looking at here, and we're using that so that we can see these inherent cores and the oscillatory rims within those grains. We want to see those boundaries so that we know where we're actually putting those spots with the laser. So then on this computer here, this is where we've actually chosen our spots, and the run is already going. So now you can see the laser is actually firing in that one spot. And using that with our CL image, we can tell exactly where we're shooting. In this rhyolite, we picked about 100 spots with standards. And because it's all automated, you can actually do that virtually. So you, as the user, could pick your spots at home or in your lab, and then we're here rotating those samples and keeping the instrument running.
So in addition to the multi-collector mass spectrometer that we have next door, we also have a single collector mass spectrometer at Arizona LaserChron. And this machine works more or less the same. So we have the same laser setup, the same plasma setup, but instead of having multiple detectors, this machine only has one. And we change magnetic settings throughout the run to sweep across different isotopic masses through time, allowing us to measure different trace and rare earth element chemistries in addition to our uranium lead ages. Now this is really powerful because it lets us look at long-term tectonic processes and things like magmatic differentiation in addition to our uranium lead ages.
I'm Kurt Sundell. I'm a postdoctorate here. And the main things that I've been working on are new methods of data visualization, data reduction, and cyber infrastructure. So for example, we have here a new data reduction platform that we can use to calculate an age for this rhyolite. Okay, so I've loaded up the raw data from the mass spectrometer. When I click reduce data, here you see all of the information that you would ever need to see during a session, and most importantly for us, the age of this rhyolite. As you can see, there are two main age modes here, one at around 72 million years and one at around 74 million years. Okay, so this is just one sample that contains around 100 ages. And so something that I've been pushing on is how can we generate data even faster? So here's an example of a session that we ran that took the same amount of time, but now we have over 1,000 ages. And so the reason you would want to analyze so many grains for a sample is because this particular sample is extremely complex with multiple different age modes. So the exciting things that are happening in the lab right now are we're taking these techniques and expanding into different mineral phases and different isotopic systems to learn even more about Earth systems.
So now you've seen the entire process, from collecting the rock in the field, to extracting the zircons out of the rock, to running the analyses on our state-of-the-art instrumentation. But this map behind me gives you an idea of the scope of the research that is conducted here in our facility. All the way from characterizing ancient trade routes in the Solomon Islands in the Southwest Pacific, to uncovering the earliest human remains in Ethiopia, all the way to the far reaches of the Arctic, Antarctic, and then of course at home. So you see our research covers the entire globe. I hope you're as excited about this as we are, because this is fun stuff. And I'm looking forward to working on projects with you in the future.